Hello, my name is Connor Badowich, and this is my ENGR 459 Advanced Electromagnetics video. I'm here today to talk to you about the wave equation and plane wave solution in regards to Maxwell's equations. So to start out, I'm going to give an intro to waves. And of course, the most fundamental question with waves is the question, what is a wave? Well, waves we see every day of our lives. In water, we see it, puddles, lakes, rivers, streams. However, we probably don't put a lot of thought into what a wave is. Well, some very smart people over the last couple centuries have come up with the definition of a spatial disturbance that propagates at some velocity. And is usually characterized as a function of both space, so x, y, and z in Cartesian, and time, t. Or more generally, it can be characterized as some function of a vector of space and time. So you might be like, what does this all mean? What does a spatial disturbance that propagates at some velocity look like? Well, to help visualize that, I can draw out some axes. Along this axis, we have space. And for this example, I'm just going to use the variable z. So this is space in the z direction. And this is going to be the wave function of variable z and time t. Now this function can take any shape, any size, doesn't really matter. For this example, I'm just going to keep it simple and make it a triangle. Now this is the function of z at some time t equals 0. So this is what the wave looks like originally. It's at some point in space, and it's at time t equals 0. Now if we take a snapshot of it at a later time, this is now the wave function of z at some time t equals t1. So you can see that it's moved through space as time has progressed forward. Now, this distance that this has traveled is characterized by the velocity at which the wave travels. So v is for velocity. So you can see that the wave is some disturbance of space, and this can be any shape, that propagates with time at some velocity. Now, you might be wondering, why are you talking on about these waves, and what do they have to do with electricity and magnetism? Good question. We start by looking at Maxwell's equations, the fundamentals of electricity and magnetism. So, just a quick summary of them all. We have Gauss's law, which states that the divergence of the electric field is equal to some charge density, which basically states that if you have some particle of charge plus q, that an electric field is going to radiate outwards from it. We also have the magnetic version of Gauss's law, which simply states that there are no magnetic monopoles. If you consider a bar magnet with a north and south pole, we know that the magnetic field actually loops around and is a closed system. There is no outward direction for the magnetic field. We have Faraday's law of Maxwell's equations, inspired by Faraday's experiments at the time, which links a changing electric field with a changing magnetic field through a constitutive relation of mu, or the permeability of a substance. We have Ampere's law, which relates a changing magnetic field with a changing electric field, and this relates it through a couple of currents. We have J, which is a conduction current. This is your standard current. If you think of a wire carrying electricity, it's a physical movement of charge. So we have here physical movement of charge. Is the conduction current. And then we have here this term with the changing electric field. Maxwell actually coined this as the displacement current, which you can think of as a capacitor. You have a current coming in I and you have a current leaving I, but you know that no physical charge is actually being moved within the two plates of the capacitor. You're simply charging the one plate as a positive Q and the other is becoming negative, and thereby you're inducing this displacement current. Now, the two terms that we're most interested in are Faraday's law and Ampere's law when it comes to wave equations and plane waves. Now, we start with the assumption, in order to move from Maxwell's equations to wave equation, we're going to assume simple media, which in Maxwell's equations, we're going to assume J, the conduction current, is 0. We're going to assume there's no charge density, so the divergence is 0. And we're just going to assume that the permeability and permittivity are that of free space. So here we have Faraday's law, and here we have Ampere's law. You can start with one or the other. It does not matter, you'll come to the same result. For this example, I've started with Faraday's law, and I've started by taking the curl of Faraday's law. This comes down, you then have the curl of the electric field, which relates to the negative derivative of time with respect to the curl of h. You simply move the curl in. Now you notice here we have a curl of h, and with Ampere's law we have a curl of h, so we can actually sub this into this equation on the right hand side, so that simplifies nicely. On the left hand side we have the identity that the curl of a vector becomes this expression here. We also know, because the charge current, or the charge density, is 0, that the divergence of E is actually 0. So this simplifies nicely down, and what we're left with is the second spatial derivative of the electric field is equal to this relation times the second derivative with respect to time of the electric field. We also know that the permeability and permittivity of free space are related to the speed of light through this expression here. And we can then sub that in to actually result in the final equation of the second spatial derivative of the electric field is equal to a relation of 1 over c squared times the second derivative with respect to time of the electric field. And this is what we call a wave equation. It simply states that a change of time on the left-hand side, a change of space on the left-hand side will result in a change of time of this function, or the electric field in this case. And the relationship between the two is characterized by the velocity at which it's traveling at. For simple media, this is the speed of light, c squared. We can do the exact same process as I have above, starting with the curl of Ampere's law, and we will result in a very similar equation. These are the general forms for the wave equation for Maxwell's equations. However, these equations don't tell us a whole lot aside from a change of space will result in a change of time. In order to find the plane wave equations, we can actually simplify this down further by using the time harmonic Maxwell's equations. So time harmonic simply means that the function is periodic with respect to time. So we can actually write the electric and magnetic field as follows. The electric field is some magnitude with respect to space times a time harmonic exponential function. This just means that you have some magnitude in some direction which wiggles with respect to time. The magnetic field is the exact same way. Now you can take these two equations and plug them into Maxwell's equations. So we have here Faraday's law and Ampere's law. We simply sub these in, and the derivative with respect to time of an exponential simply brings down the e to the j. So we have here a partial derivative with respect to time of e to the, not negative, j omega t. This is simply equal to j omega times e to the j omega t. So that's all I did here. I plugged these into these equations, and what you're left with here is the time harmonic version of Maxwell's equations relating the electric and magnetic and electric fields. Now that we have the time harmonic versions, you can actually use the exact same process as I used on the previous page, where you take the cross product and sub it in, and you get two very similar equations. These are the time harmonic wave equations of Maxwell's equations, and these are actually specifically known as the Helmholtz equations. Why did we simplify these down using the time harmonic? Because when we plug in the plane wave solutions into these equations now, we'll be able to determine some relationships between the electric, the magnetic, and the direction of propagation of what a plane wave is. So next here we have the plane wave solutions. Plane wave solutions are characterized as a complex exponential function. So here we have the electric and magnetic field, again, with a magnitude and a complex exponential, but instead of simply being wiggling with respect to time, it wiggles with respect to space and time. So in this equation here, we have the vector k, which is actually known as the wave vector, which is some spatial frequency in the x direction, kx, spatial frequency in the y direction, ky, and kz. And r, this is the dot product, r is simply the direction of propagation, and in this case, for Cartesian, it's some x, y, z components. So what we can do is actually take these plane wave solutions and plug them back into the Helmholtz equations. So here I have the Helmholtz equation for electric field, so we'll start with that, and we simply sub in E for the electric field. So there's some basic derivations that occur here. For this term, we simply plugged in this to here. We're going to ignore time for now because this is a spatial derivative. So we're just going to assume that this portion of the exponential is 0. So because the magnitude is not a function of space, we can pull it out front. We have the second spatial derivative e to the negative j kr. For simplicity, we're going to just simply let r equal some magnitude z in the z hat direction. So we just have a wave traveling along the axis of z. The second derivative, as I described here, the first derivative simply results in j omega. The second derivative, in this case is jk, simply becomes jk squared, and there's a negative here. The negative becomes a positive with the square, but the square of j is -1. Therefore, this becomes the magnitude of e times the negative of k squared times the exponential. So this is for this term. Now if I take this term and this term, we get negative k squared times the electric field plus omega squared mu naught epsilon naught times the electric field must equal 0. So we have some cancellations, the electric field cancels, and we're left with this relation, k squared equals omega squared mu naught epsilon naught. And we've already determined that the relationship between the permeability and permittivity of free space is the speed of light. This leaves us with this relationship between k, omega, and c. C being the speed of light, k being the spatial frequency, characterized by 2 pi over the wavelength, and omega being the temporal frequency, 2 pi over the period t. So this is the first important relationship between spatial frequency and temporal frequency, which we can determine from the plane wave solutions. There are two other key components, the first of which is the wave vector and its relation to the electric field. So what we can do is we can start with Gauss's law, which in this case for simple media we assumed that the charge is equal to 0. So it's 0. We plug in the complex term, the magnitude of the electric field with some complex exponential in the z direction. Again, the magnitude is not a function of space, so we can pull this out and rearrange it. And we simply take the first derivative, which becomes negative jk. And again, k is what we're interested in, so we can actually pull the negative j and this out. So what we have here is the magnitude of the electric field dot product with the wave vector, k, multiplied by a complex exponential term. Now this must equal 0. So we know that the dot product of the electric field and k, the wave vector, must be 0. Basically, this is telling us that the electric field and the wave vector are perpendicular. This is the second important characterization from the plane wave solution. The third and the last, we can then use the time harmonic version of Faraday's law, plug in the electric field solution that we have, and then solve for the magnetic field. Through complex derivation, we yield the result that the magnetic field is simply E cross product with the wave vector, the wave unit vector, and is related to the electric field by this wave impedance, 1 over eta, where eta is equal to the temporal frequency, the permeability, and the spatial frequency. Now we can see here that the magnetic field must also be orthogonal to the electric field in order for this to yield a non-zero result. So, what have we learned from all of this is that we have Maxwell's equations, which can be simplified using the time harmonic and simple media assumptions to gain the Helmholtz equations. And from the Helmholtz equations, we can sub in the complex exponential solution for plane waves. Which shows that the electric field varies with space and time. And we've come to the conclusion that the electric field is perpendicular to the wave vector, or the direction that it's propagating, and the electric field is orthogonal to the magnetic field. Knowing that these three components, the electric field, the wave vector, and the magnetic field, are orthogonal, they actually become they follow the right-hand rule quite nicely, actually. So to visualize this, what I have here, there are three axes. This long axis will be the wave vector k. This is the direction that the wave vector k is pointing. We then have the electric field, which is orthogonal to k, and therefore, by the right-hand rule, we must have the magnetic field pointing in this direction. We then know that the electric field is varying along this axis with respect to time and space, and it has some magnitude E0. I can draw it out. And the direction of motion is this way at some velocity. We then also know that the magnetic field, through the right-hand rule, also propagates in this direction, but is orthogonal to the electric field. And it moves at the exact same speed v. Its amplitude is related to the amplitude of the electric field divided by the impedance of the media that it's traveling in. So, to summarize, Maxwell's equations can be used in a time harmonic form to simplify to Helmholtz equations, which then we can plug the plane wave solution of a complex exponential electric field into the Helmholtz equations to determine the relationship between the wave vector k, the electric field E, and the magnetic field H. And all of this math gives us a wave that propagates through free space or any media that remains orthogonal to each other, the electric and magnetic field, and propagates at some velocity v. We also define the points between two peaks or two troughs as the wavelength. And k, the magnitude of k, is related to it by 2 pi over the wavelength. That is a video explaining electromagnetic waves.